Okay, so hi everyone. Today we are talking about the biohydrogen production as a clean energy source on Mars. I'm Zongxi.
I'm Taylor Pinkerton.
Chloe Simchick.
And I'm Elle Berger.
So now I'm gonna start with a basic overview of Mars. So being the fourth planet from the sun, Mars is a dusty and cold world. It is known as the red planet because the iron materials in the Martian soil oxidize or rust, causing the soil and the atmosphere to look red. The Martian atmosphere is very thin and it has a very different composition compared to Earth's atmosphere. About 96% of the air is carbon dioxide. The surface of Mars is rocky and rugged due to the volcanic activities, impacts, winds, crustal movement, and chemical reactions. Based on these facts, we can see that the environment on Mars is not suitable for the living of lives. And now we are facing a couple of challenges in exploring Mars. First of all, people have to live under unfavorable conditions, including the air that mainly consists of carbon dioxide, the rather small gravity, which is 0.7375 that of Earth, and the low temperature, which averages around -63 degrees Celsius. And apart from that, we have to find supplementary water source because most of water present on Mars now is in the form of ice. Although the International Space System uses a water recovery system that recycles pretty much all of their liquid waste with a recovery rate of around 93%, we still need a supplementary water source eventually. Also, we need to figure out how microbial systems can utilize alternative feedstocks such as carbon dioxide, human waste streams, and regolith for growth and production performance. Last but sure not least, we need to grow plants on Mars to get food. Despite the fact that the soil of some areas of Mars is toxic, we still have to introduce specific bacteria to improve Martian soil.
Yes, so there's lots of things that need to be done to be able to create fuel on Mars. And one of the most promising is biohydrogen production for a low carbon Mars fuel source. So this can be derived from many sources such as biomass, natural organic matters, organic waste, and industrial wastewater. And biohydrogen can then be produced via biophotolysis, microbial electrolysis, fermentation, or thermophiles, which is then purified by chemical absorption, membrane separation, cryogenic separation, or absorption. And biohydrogen applications can be used in transport, electricity, industrial feedstock, heat, or alternative fuel, which are all things that we'll need on Mars to sustain life. And so for the purpose of this presentation, we're going to focus in on fermentation. So biohydrogen can be produced via dark fermentation, as seen in the reaction on the top, where the substrates of organic and inorganic matter is shown on the bottom left, such as agricultural waste, fruits and vegetables, industrial wastewater, and human waste, can all be converted to pyruvate with the byproducts of NADH and carbon dioxide via the glycolysis pathway with anaerobic bacteria. Furthermore, this pyruvate can then be converted to biohydrogen or other bioorganic products using iron-iron or nickel-iron hydrogenase. And these other bioorganic products on the bottom right are ethanol, butanol, formate, and butonic acid. So some of the dark fermentation key parameters are as follows. First, it uses the absence of light and oxygen, which helps and is suitable for an environment such as Mars. Secondly, a pH of 5 is ideal because extreme levels inhibit hydrogen production by affecting growth and hydrogenase enzyme activity. This and the temperatures between 20 to 60 degrees Celsius which is a bit higher than the typical Mars climate, can be controlled via a simple reactor design. Next, a higher carbon to nitrogen ratio can be used to prevent microorganism death from ammonia. Next, a pretreatment of biomass, microorganism, and sugar content is crucial to increasing the efficiency. And lastly, the reactor needs to be designed for optimal partial pressure to increase the yield. And this can be achieved by partial pressure maintenance or continuous removal of hydrogen. So dark fermentation has numerous advantages, such as the following. It not only is cheaper because it has a simple reactor design and uses various inorganic, organic matters. It's also environmentally friendly, and it helps with waste management by using various wastes. And because it does use these wastes, it is nutrient dense and packed with carbohydrates, proteins, and more. Furthermore, dark fermentation can use single or mixed cultures depending on the waste source that is the input. It is also low energy and it yields a high production. While dark fermentation has numerous advantages, one of the disadvantages is its yield. Dark fermentation on its own produces 4 hydrogen per glucose maximum. However, we can see that a combination of dark and photo fermentation can maximize yield and triple that amount to approximately 12 hydrogen per glucose max. And this can be completed in sequential reactors to maintain optimal conditions for each. So as you can see, the effluent from dark fermentation goes into photo fermentation, and it's critical to neutralize and dilute this effluent to increase yield, although that will lead into an increase in energy consumption and decrease in productivity. And now my colleague will talk more about the combination of both and the microbes to be used.
Many kinds of microorganisms can be used for these fermentations, but facultative anaerobes and obligate anaerobes are preferred, with photosynthetic organisms that operate under anoxic conditions used specifically for photofermentation. For dark fermentation, the most commonly studied mesophilic organisms are Clostridium, Enterobacter, and Bacillus. Photofermentation utilizes purple sulfur, purple non-sulfur, and green sulfur photosynthetic bacteria, including Rhodobacter, Chlorobium, and Rhodospirillum. The bacteria used in both dark and photofermentation can use a variety of organic wastes as substrates, such as fruit and vegetable wastes, agricultural waste, and sewage sludge without oxygen, making them suitable for degrading organic compounds from human waste and from food, and agricultural waste produced from Martian farming, once that form of farming has been established. From the organic wastes fed to the bacteria in dark fermentation, the main products that are formed are metabolites vital to biosynthesis. The intermediate pyruvate is produced from organic wastes via glycolysis, which is then converted to several kinds of organic acids. Some pathways forming these metabolites, such as the acetic acid and butyric acid pathway, are hydrogen-producing pathways, but others like the malic acid and propionic acid pathways are hydrogen-consuming. The hydrogen yield in dark fermentation is low because of the formation of byproducts, but the metabolites produced can be fed to another reactor to sustain the growth of photosynthetic bacteria, which can produce a higher yield of hydrogen via photofermentation. Photofermentation can utilize organic wastes and metabolites from dark fermentation, plus light and water, to produce hydrogen through nitrogenase activity. It has been observed that in the absence of nitrogen gas, nitrogenase will reduce protons to hydrogen gas using ATP, which is generated through the capture of solar energy. The Martian atmosphere, being mainly carbon dioxide instead of nitrogen gas, like the Earth's atmosphere, would be advantageous to this process. High yields of biohydrogen have been observed with photofermentation, but there are also challenges such as transparent reactor design, water sources, and poor light conversion. Additionally, hydrogen yield is proportional to light intensity, and the intensity of sunlight on Mars is lower than that of Earth, so less ATP would be generated to use in the conversion of protons to biohydrogen. Since yields may still not be high even when integrating dark and photofermentation, There may be some benefit in focusing on increasing yield of biohydrogen by manipulating dark fermentation. Certain trace elements have been shown to produce a higher yield of hydrogen in dark fermentation, including iron, which could be obtained from Martian regolith. Studies have shown that under optimal conditions of ferrous iron, the expression of hydrogen-consuming and non-hydrogen-producing pathways is decreased, while the expression of hydrogen-producing enzymes is increased. Additionally, certain products, such as propionate, are converted to hydrogen in the presence of ferrous iron. Other forms of iron have also been shown to induce a metabolic shift to produce a greater yield of hydrogen, such as ferric oxide nanoparticles in elemental iron. Martian regolith is estimated to contain, on average, 17% ferric oxide, which can be extracted through means such as bioleaching, by iron oxidizing and iron scavenging bacteria, followed by other processing steps like precipitation and magnetic extraction. From there, ferric iron must be liberated from the ferric oxide and then can either be reduced to ferrous iron or chemically converted to ferric oxide nanoparticles. Each route has its inherent challenges, but if either form is added to a culture, ultimately hydrogen production is increased. And now I'll pass it to my colleague to talk about economic analysis.
Thanks, Chloe. So Mars has been in the news lately for being another planet that could host life. Innovators like Elon Musk helped bring interest to this topic. Per Statista's projections, there has been roughly $16 billion dedicated to exploring Mars. And if we plan to eventually move to Mars, we are going to have to be forward-thinking in ways we can generate power. Per Inverse, Elon Musk estimated in 2019 that it would take around 1 million tons of cargo to build a self-sustaining city on Mars. Assuming it costs $100,000 per ton to send cargo to Mars with the upcoming Starship, that would put a Mars city's price at around $100 billion. At the high end, Musk estimates it could cost around $10 trillion. Since the price of transporting heavy fuels such as coal is so expensive, this does not make fiscal sense to transport coal to produce energy on the red planet. This opens the door to explore viable biohydrogen sources of energy that require little to no money besides equipment weight to transport. According to the United States Department of Energy, outside data shows that hydrogen can be produced today within a cost range of approximately $2.50 to $6.80 per kilogram from a mix of renewable and grid feedstocks. This is in good alignment with the Department of Energy analysis, which shows that hydrogen can be produced via PEM electrolysis at a cost of approximately $4 to $6 per kilogram for specific conditions. If we use Musk's projections and the amount of coal we use a year per Forbes, we burn 8 billion tons of coal per year. If we take this into consideration, 1 year supply of coal, which only supplies roughly 1/3 of our total needed energy to power the world according to Forbes, would cost $800 trillion to transport, which is 80 times the amount of money it would take to transport the amount of supplies needed to build the Mars city. Where hydrogen fuel would only cost approximately $17 trillion to produce. In contrast to biohydrogen, there are viable fossil fuel energy sources that weigh considerably less than coal. An example would be liquefied natural gas. Thank you so much for listening to our presentation about biohydrogen production as a clean energy source on Mars.